Hey everybody, welcome back to Environmental Organic Chemistry with Lisa. It's good times down on the farm. I'm trying to figure out how to get this stupid Kaltura thing to work. Okay, there we go. So in this part of the hydrolysis lecture, we're going to talk about Sn1 and Sn2 reactions. And I hope that if you remember nothing else from your organic chemistry class, perhaps you took it with Dr. Boykus and you remember nothing else, but you remember about Sn1 and Sn2 reactions. And you hoped that you would never, ever hear about them again. But here we are, we're going to talk about them. It turns out Sn1 and Sn2 reactions are quite common and important in the environment because they involve nucleophiles, where the nucleophile could be water or hydroxide. And of course they involve leaving groups, where the leaving group could be chloride or bromide. And of course chlorinated compounds are quite common in the environment. So it's very typical that you will see these kinds of reactions. Okay, and we have these wonderful YouTube videos for you. So here's the Sn2 reaction. And I like to show this for you because this is, just gives you a nice visualization of what's happening in this system. I know that you can't hear the system video, and I can, and so it's very confusing. I'm trying to talk to you over this other guy, and if I mute him, I mute myself too, and I can't figure out how to not do that. Anyway, so in this particular animation, they're showing that the nucleophile is hydroxide on the left, could also be a water molecule, and it's going to come in and it's going to attack the bromoethane. The bromine is the yellow thing. And as those electrons from the hydroxide go and attack, you can see on the right how you're getting toward that transition state complex. So this is the most, or the highest energy form. This is the activation energy. This is the highest hill that you have to get over in terms of energetics. And it's where you have that pentacoordinated carbon intermediate. And then as the bromide leaves, you start falling down the slope again, and you get down to your products. I believe they're going to show you that one more time. Yep, one more time. So here you are, you're on the roller coaster, and you start going click, 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 click up the side of the hill. You reach the top of the hill, and you're suspended in midair for a moment of weightlessness. You're at the highest energy state, and then whee! Down we go the other side of the hill, down to our most stable energy state. So that is the Sn2 reaction. And so we remember that Sn2 stands for substitution nucleophilic bimolecular. And similar to what we just saw in the video, you've got your nucleophile attacking your substrate here, forming your transition state complex, which has carbon with 5 bonds to it. 1, 2, 3, 4, 5 bonds. Carbon is not happy in that 5 bond state. And so that's a very strained, very sterically hindered, very sterically crowded transition state, and so it wants to get rid of something, and the best leaving group is the one that's going to have to go, and it ends up lost over here. And so the Sn2 rate is going to depend on the strength of the nucleophile, because the nucleophile is involved here in the intermediate, in the transition state. It depends on the charge distribution at the reaction center. It depends on how good the leaving group is, whether it's happy to leave. And it depends on steric effects because that pentacoordinated thing is very, very sterically crowded. So for leaving groups in water, in the environment in water, iodine and bromide tend to be the best leaving groups. Chloride is a pretty good leaving group, and fluoride is actually not a very good leaving group in water. You know, if you go look at Khan Academy or something online, it will give you a different order for leaving groups here, but that's because they're considering solvents other than water. Fluoride is very highly solvated by water molecules, and that's why it's not a very good leaving group, because to leave, it's not solvated by water molecules when it's in the act of leaving, so it's very unstable and doesn't want to do that. So it doesn't make a very good leaving group. So the rate law is, dC dt, where the concentration here is the concentration of the chemical that is being hydrolyzed. So dC dt is equal to the rate constant times the concentration of the substrate times the concentration of the nucleophile. So this rate constant, of course, is a second order rate constant and would have units of something like per molar per second, right? Capital M for moles per liter, molar per second. So it's got second order rate constant units. Now, if the nucleophile is water, we can assume that the concentration of water doesn't change. And so we could collapse this down into a pseudo first order rate constant. By the same token, if the nucleophile is hydroxide, but the pH is not changing, then again, we can assume that we can treat this like a pseudo first order reaction. If we're in seawater and the nucleophile is chloride, that's always going to be at 0.5 molar, so we can treat it as though the nucleophile does not change in concentration, and we can treat this as a pseudo first order process. The other important reaction mechanism is the Sn1 mechanism. This is where the leaving group unilaterally leaves before the nucleophile ever gets involved in the process. So it's like when you break up your marriage, not because you're leaving for someone better, but because you just can't stand your spouse anymore. So the transition state here has to do with the stretching of that carbon to leaving group bond, but the nucleophile is not involved here anywhere. And of course, the steric hindrance is not nearly as bad because you've only got the 4 bonds to carbon. And we have a fancy video for this one too. So the video is talking about how what you're looking at is bromoethane, which is the same chemical you saw in the previous video. That chemical would go by an Sn2 mechanism. But if you replace those hydrogens with methyl groups, now you have a much more sterically hindered carbon there in the middle. And so the Sn2 mechanism isn't going to work anymore. So those bulky, as you can see in the captions, the bulky alkyl groups do not allow attacking species to approach the central carbon. And you can see by providing that halo, it's showing you really what the size of this molecule is. And the nucleophile just can't get in there. So again, we're going to use hydroxide as our nucleophile, but that's not important right now because the first step is where the carbon-bromine bind has to break first. And so that's the transition state complex. That determines the rate-limiting step of the reaction. So the bromide just leaves all by itself, and you get your friend, the carbocation. Now in this animation, they're showing that the carbocation gets captured by hydroxide. That's realistic, except that in water, there's a lot more water around than there is hydroxide. So in fact, the carbocation gets captured by a water molecule, not a hydroxide, but the end result is the same. You're going to get the alcohol. So up the side of the hill, whee, down a little hill, and then up to the EA2, which is less important, and then whee, down the other side of the roller coaster. So good times. Okay. So for the Sn1 mechanism, again, leaving group leaves first, leaving behind the carbocation here, and then the carbocation will be caught by whatever nucleophile happens to be around. In our world of environmental chemistry, the nucleophile that's almost always around is water, so this thing's going to get captured by a water molecule. And notice that the water can attack from either side, and so that can scramble the stereochemistry. Sometimes that's important for environmental chemists because sometimes we do like to use stereochemistry as a way of tracking chemicals and figuring out what's happening to them in the environment. Okay, so the rate determining step is the formation of the carbocation. And because of that, this chemical reaction, this type of mechanism, is important for, not so much for secondary halides, but it tends to be more important for tertiary. That's what you saw in the video. Tertiary means that the carbon has bonds to 3 other carbons, and then the 4th bond is to the leaving group. And it's also important for allylic and benzylic halides, and I'm sure you don't remember what those look like, so I have that here. So an allylic carbocation is where the carbocation, the cation part, is 1 carbon over from the double bond. And sometimes you may have seen this in your chemistry textbooks drawn like this, where you have the little dotted line and a positive symbol here, because that positive charge is resonating back and forth across all 3 of those carbons. And that's just another way of drawing the same thing. And then this is benzylic. That's where the carbocation is 1 carbon removed from the benzene rings. And so this is an sp3 hybridized carbon, sp2 hybridized carbon. You remember that from Orgo, right? The carbocations, like this one, are sp2 hybridized, and double bonds are sp2 hybridized. And so that allows the electrons to resonate between all of these orbitals. Same thing is going on here. Each of these carbons is sp2 hybridized. And so the electrons are able to swim around the ring and also resonate into the carbocation. And that makes it much more stable. Those electrons are alleviating the fact that this is a positive charge. And so in other words, they're spreading the positive charge out over the ring, and the more you can spread it out, the more stable that carbocation will be. So these Sn1 mechanisms are most common for things that can form stable carbocations, and that would include benzyl halides, allylic halides, tertiary halides. And the rate depends on the goodness of the leaving group and the stability of the carbocation, but the nucleophilicity of the nucleophile doesn't matter in the slightest. And in fact, the nucleophile is almost always, in our case, going to be water. So the rate law is just the change in the concentration of the substrate over time is equal to the rate constant. This is now a true first order rate constant multiplied by the concentration of the contaminant. And as a true first order rate constant, this will have units of 1 over time, like 1 over seconds.